Good morning, everyone. So we are now on some other rules on probability. This time, specifically on what we call addition rules, right? So a keyword for addition rule is the word or. Right? Okay. So if you see the word or, then that means that's the probability that the first event or the second event is going to happen. So this occurs if you have multiple events and you want either or both events to happen. Again, the word is or keyword is or. But before that, let's consider first our review from yesterday's and some other details about basic probability rules. The first one is what we call our fundamental counting principle. Okay, let's read this one first. Our fundamental counting principle. Brittany, go ahead, please. Right. If there are
If there are n outcomes for event 1 and n outcomes for event 2, then there are n times n outcomes for both events.
Thank you. In short, you're simply going to multiply the how many outcomes there are for both events 1 and 2. So again, you basically multiply them. Okay. So again, we did that one yesterday on our one of our probability rules from yesterday, and I did mention something about fundamental counting principle, and this is the official statement regarding that principle. Okay, you simply multiply the outcomes of each event if you want to consider both events happening. Okay, and again in this case also we need to consider what we call yesterday we did something about what no repetition of events, all right, or outcomes, and there are two ways for such: either they're ordered or no ordered, right? So when you say ordered, that means there's a first pick, second pick, third pick, fourth pick, and so on. So if there's an order for such, then that means that is called permutation. And what's that? That is NPR. That's the number of elements chosen in order. So there's a first pick, second pick, third pick, or fourth pick. However, if you are choosing elements with no repetition as well, but order is not necessary. In short, you're basically grouping, for example, if there are 10 students, you're grouping, you're choosing a group of like 3 people in a group, right? So it doesn't really matter who's the first pick, second pick, or third pick. Then you're doing what we call combination. Now, how do we do this on our calculator? So here are our calculators functions for such. If we go to our Desmos and see those permutations and combinations, okay? If you go here on our keypad, okay? Now go to your functions, okay? So again, keypad, functions. After that, let's go down and see those probability tools. Okay, ready guys? Able to see that one in here? So if you go to your probability tools, you will be able to see the following. Got it guys? Okay. So once again, you go to Desmos, you go to functions, you go to the number theory, and you would see in here the following: the NPR, that's for permutation, and the NCR is for combination. And how do we use that one? Let's see. If I choose this, okay, and put in the following, let's say 10, comma, and you choose, say, yesterday we did what? 10 roller coasters, right? And how many roller coasters should you ride? 2. Is that what we got yesterday? Right? 9. Okay. However, if you're considering choosing 2 roller coasters from 10 without order, so regardless of who or where, what you ride first and what you ride second, it doesn't really matter, then that's combination. How do we do combination? Here it is. Click on functions, go down again on that number theory, and click on the NCR instead, and choose what? 10, comma, 2. Right, guys, and as you may notice, it reduced to half its number of elements or number of outcomes. Okay, so once again in here, let me just put some notations in here. This is what? Number of ways, okay, of choosing two roller coasters, okay, in order, okay, in order. From how many? 10 roller coasters, okay. This now, however, is what? The number of ways of choosing, still the same, two roller coasters. But again, I would put in here, regardless of order. So in short, it doesn't really matter which one goes first or second. Okay, you just choose two. With that being said, from how many? 10. So as you may notice, the first, your N is always how many is in your sample space. Okay? And R in how many are you choosing? Okay, so that's our probability tools, or actually a part of the fundamental counting principle tools. If you're seeing what? Order or without order, right? And again, the keyword in here is also no repetition, okay? So whatever you chose first, you cannot choose it again. Okay?
You said N is how many is in your sample space. And what did you say R was?
Yeah, N is the sample space, that's correct, for both combination and permutation. That's a good question, Obi. However, R is the what? How many elements are you choosing from the sample space? Okay, so from yesterday's, just referring from yesterday's, you have 10 roller coasters. You want to choose 2 rides, all right? 2 roller coasters out of 10. So that your R is the how many your desired outcomes will be. Any questions? Next one. So we are done with that one. We are now working on what we call complementary event. And when you say complementary event, that is the probability of the event not happening. Okay, again, if the probability of, you are looking for the probability of your desired event not happening, okay, then that is equal to what? 1 minus the probability of the event happening. So once again, when you say complementary event, that's the opposite of your desired event. Because in some cases, you wanna see what's on the other side. Okay, and how do we compute that one on the other side? Let us now consider this particular problem here, and notice how we can work on that one. Okay, so here it is. Everyone has a copy of the 5.2, all right? So this one, check on those summary and see this one, computing probabilities of complements. Let's read it first, okay? Angelina, go ahead please. The data in table 7.
The data in table 7 represents the income distribution of households in the United States in 2017.
Okay, so these are the income distribution of households in the United States year 2017, okay? So that's the annual household income, right? From what? Less than 10,000 to more than 200,000. And that's what? Annual in a year, right? In a fiscal year. That means from January to December, okay? And those are the what? The number of households, not people, all right? Although definitely there are some households that's like there's only one person in there, but there are also households that's like have extended families and whatever the household situation is. Get it? Okay. Anyway, going back in here, let's read what we're gonna do for letter A. Let's read this one. Tiff, please compute.
200,000 or more.
Okay, so 200,000 or more. How do we get that one? So what's the probability that a randomly chosen household will earn is earning $200,000 or more as an annual income? So we're gonna put in here what? Probability of what? 200K up is equal to what? Well, how many thousands of households have 200,000 or more? 8,284, that is correct. So I'm going to put in here 8,284 divided by the sample space. So how do we get the sample space? Well, we're going to add up all of those households all together, okay? So it doesn't say in here how many households are there in total. So basically, we can just get the summation of all of those households for this entire table. So with that, let's just put it in our calculator. All right, there we go. So we got what? 7804 plus 5403 plus 11166, all right, plus 10926 plus 15248 plus 21131. So basically in here, just be careful with the numbers that you're typing in, right? Okay. 15008. Okay, so make sure that you check the data that you're putting in every single time, all right? Okay. 17529 plus 7564 plus 8284. And as you may notice, that also includes the $200,000 or more. Okay, so everything, right? All households in 2017 of the entire country. It says in here, if I type it in right, and again, there might be some manual error in encoding, right? But so far, what I've seen in there is what? There are 120,063 households all in all. Okay, so that is your sample space, right? So this 8284, those who are earning $200,000 or more will be divided by the sample space. And what is that? 120, what did we say? 063. Again, always make sure that you verify what you have typed in. Okay, so there might be some manual error in like encoding, right? Which, as human as we tend to have, anyway, what do we have in there? So basically we're gonna divide them. 8284 divided by 120,063. And I got how much? 0.069. Alright, so that's 0.069 in 3 decimal places. That's the probability, right? 0.069. Let's maybe put that one here. Approximately 0.069. Or you can say what? 7%. Okay, if you multiply it by 100%, that's 7%. As you may notice in statistics, that's also called our relative frequency anyway. Okay, so as you may notice, it's like if you do the stat crunch, do the relative frequency distribution for this data, you would get the same result. Okay. Next one, letter B. Let's read letter B in here and see how we can work on that. Okay, JC, let's read letter B. Less than 200,000. So how do we do that one? Okay, so here it is. When you say less than 200,000, instead of seeing all of these in here, because these are all the less than 200,000, I can simply use the what? The complementary event. Okay. Why? Well, if I say in here, well, the probability of less than 200,000 is actually equal to what? 1 minus the probability that is actually what? Greater than or equal to 200,000. If you get what I mean, guys? Yeah. Okay, once again, since we already know that the probability that the household income greater than or equal to 200,000 is what? 0.069. Then the less than 200,000 is what? The complementary event for that, right? So with that being said, then the probability of less than 200,000 basically will be what? 1 minus the probability of what? This one, right?
Yep.
Okay. 200,000 and up.
So you just switch it.
You just switch it, right? According to your complementary event. Why? Because these two are complementary events. They are opposites, right? What is the opposite of greater than or equal to? Less than. Okay. And that's it. What will be your answer? 1 minus 0.069. Questions? Okay. And what's that going to be? 1 minus 0.069 will be how much? Well, a while ago we said 7%. So something like what? 93%. Okay. Well, let's see. 1 minus 0.0669. Okay. That's what? 93%. Okay. So I'll put in here 0.931. Okay. So what's the good deal with this? The good deal with complementary event is what? Well, when you say less than 200,000, you don't need to what? You don't need to add this, and everything in here over that just to get that. Why? Well, you already know what this one is, right? Then yes, just use the complementary event for them. Get it? Okay. So it saves you time and it gives you a little bit more in-depth analysis about probability. Last one in here, letter C. Let's read letter C for such. Sydney, go ahead, please.
At least 10,000.
So how do we use that one? At least 10,000. So when you say at least 10,000 in inequality notation, how does it look like? Let me go ahead and use this green for that, okay? The probability, it's at least 10,000. So that's the least, right? So that means that's what? Greater than or equal to 10,000, right? Because the 10,000 is the minimum. You want it to be, equal to or more than that. Okay. So how do we get that one? Well, that will be, according to complementary event, will be what? 1 minus the probability that it's what? What's the opposite of greater than or equal to 10,000?
Less than.
Less than 10,000. All right, that's it. So what's that? 1 minus, so what is 10,000 less than? 7804. Okay, that's it. So 1 minus 7804 over, what's the total household again? 120,063. Okay. So when you say at least 10,000, you don't need to do this, everything in here, add them up, and divide it by 120,060. That's a lot of work. By complementary event, it's easier to do it that way.
Where did you get the 120?
Okay, that's a good question, Sydney. Where did we get the 120,063? We added up all the households, right? Regardless of the annual income. Okay. In short, that's what we call the sample space. Okay, NS. Anyway, let's put it in here as follows. 1 minus, what's that again? 7804 divided by, once again, 120,063. Okay, and that'll be our answer, 0.935, right? Okay, as a probability is 0.935. In terms of proportion or percentage, we can say that 93.5%, okay, is that. Questions with our complementary event. The advantage of complementary event, it eases our repetition on computing, okay? But gives us a more in-depth analysis of probability at the same time, okay? So a double advantage for us, okay? Now, the last one is what we call our general addition rule. So this is our general addition rule, guys. So check it out in here. What does it say? That the probability of events A or event B happening is equal to what? The probability that event A will happen plus the probability that event B will happen minus the probability that both events will happen. However, in some cases, this will be equal to 0, right? And why will that happen, right? Well, it says in here, if the probability of A and B both happening together is equal to 0, that means they are mutually exclusive events. There's no way that events A and B is going to happen at the same time.
Wait, can you say that one more time?
All right. Again, if there is no way that events A and B will happen at the same time, then they are called what we call mutually exclusive events. For example, if you have blue balls, red balls, green balls, white balls, what is the probability that if you pick one ball, it will be red and green at the same time? 0. Very good, right? Then that means picking of a ball is what? Mutually exclusive event, right? There's no way that you're gonna pick a ball that has the same color, let's say, red and green. Get it? Okay. But again, if that will be the case, then that will be 0, then that will be disregarded already, right? However, there are some cases that it's not mutually exclusive. That's why it's in there, to generalize the addition. Okay? Now let's say in here, what do we do for this one? So let's consider this particular problem and see how we can work on this one, okay? Okay, this is on our practice guide. Driver. Okay. Well, sorry for those who have, some people have experienced these, and it's an occurrence, natural occurrence when you are driving, right? So, yeah. Let's read our driver fatalities, okay? Let's read this one first. Obi, go ahead, please. The following data
represent the number of drivers involved in a fatal crash in 2016 in various light and weather conditions. Should I keep going?
Yes, please. Letter A. Thank you.
A. Determine the probability that a randomly selected fatal crash in 2016 occurred in normal weather.
Thank you. All right. So again, this is seeing the the weather, right, and the light condition, right, as factors on the fatalities of the driving accident, right, or crash. Okay. Okay. Now it says in letter A, determine the probability that a randomly selected fatal crash in 2016 occurred in a normal weather. Let's call it what? Probability in a normal weather. So PN. Let's call this one. This N. Let's call this N. Right. So that means in here, the probability of being in a normal weather is what? Well, normal weather, where is that? The first row, right? So what you gonna do with those? Add them all up, right? So let's add them all up and let's see how many we're gonna get. Okay, so we need to type it in like really quick in here, guys, and see what do we get from here, okay? Where is that? Okay. 29,581. Thank you. Okay, so 29,581. So that is the total of, let's call it, summation of N. All the normal weather fatalities. We got 29,581. Okay. Now what do we do with the rest? So basically, we're gonna do that one for the rest of them. Okay. To get the total first. Okay. So can I assign this one to you guys and have your numbers in there? Okay. So this group in here, Avi's group, rain. Okay. Snow, sleet in there, Angelina, Roby's group, and in here, can we get the snow and sleet? Okay, Mason, Obi's group. Others, all right, can we go in there? Emma and Journey's group, okay. And unknown, can we go there? Mia, Juliana's group, all right, for the unknown. Okay, so let's see. How much did you get for the rain total? Summation R. 2,000 what? 2143. Thank you. Summation S. Snow and sleet. Is that 2148? Okay. Again, and in here there might be some encoding error as well. Okay, so mind you guys. Okay, snow and sleet. Where did I get that one from? Okay. 445. Thank you. About others, what do we got? 448. Thank you. Right.
That's what I thought.
448. And unknown.
1817.
1817. So, the probability that occurred in normal weather is what? 29581. That one over what? Well, we add them all up, right? So let's add them all up and let's see how much we get out of all of this, right? That will be our total driving fatalities, right? Regardless of what? Light condition and regardless of weather, okay? Okay, how much did we get? 34,439. Thank you. So I'm gonna put that one in here. 34,439. And let's see. Okay, so assuming that all of those numbers are correct, we should be seeing. Okay, so what's that again? 29,581 divided by 34,439. 34,439. And we got how much? 0.8589. Okay, 0.8589. So if we go back in here, oh yes, we got it right? 0.859. Okay, so very good. We are good with that, which means that we got our adding up in here correct. Let's read letter B. Let's read letter B. 3. Go ahead, please.
Determine the probability that a randomly selected fatal crash in 2016 occurred in daylight.
In daylight. Okay, so we're gonna consider the daylight. Where is that daylight? See that one in here? Okay. Well, what we're gonna do? We're gonna add all of those, right? Let's call it daylight. Summation dy. So can someone add them up for us? 14,307, 875, 219, 125, and 810. So again, regardless of weather.
16,336.
16,000. Okay, let's put it here. 16,000. 336. Thank you. All over the same 34439. Okay, and that's the probability of what? Let's call it dy, daylight. Okay, and what do we got? Can you verify? What's that? 16,336 divided by 34439. Did we verify our answer to be 0.474, guys? It is? Okay, thank you. That is correct. 0.474 again, just basically approximating, okay? And letter C. Let's read letter C in there. Brett. Okay, let's see. Letter C.
Determine the probability that a randomly selected fatal crash in 2016 occurred in normal weather and in daylight.
Normal weather and in daylight at the same time. So where's that normal and daylight? So as you may see, normal and daylight, that one, okay? Get it? Okay, so that's it. What's the probability that is normal and at the same time daylight? So that's what one? 14,307 divided by how much? 34,439. And how much is that?
0.418.
418. Okay. So in there it says 415 or 418. Yes. Approximately. Good. And the last one, letter D. What is the probability that the fatal crash occurred in normal weather or in daylight? So that is our general rule, and here it is. Probability normal or daylight is equal to what? The probability that's normal, 0.859, plus the probability that is daylight, 0.474, minus the probability that it is both daylight and normal weather where it happened. And how much is that? 0.415, okay? And again, this is the one. And daylight. And how much is this? Verify, what's that gonna be? 0.859 plus 0.474 minus both of them happening. Verify, did we get the 0.918 for that, guys? Yes, did we do? Again, this comes from the normal, that's our normal weather. This comes from all daylight weather. But the subtraction comes from both of them happening at the same time, which is what? 0.415. Okay? Questions with what we did? We're gonna continue with this general addition rule by tomorrow. But again, the formula is basically that, right? Probability n plus probability daylight minus probability of both happening. In short, that these two events are what? Not mutually exclusive. Okay, again, these are not mutually exclusive because the both of them happening is not equal to 0. Okay? Tomorrow is another day for this one, but just giving you the rest of the formats. Thank you.